Steppeler's talking this morning. For those of you who don't know, Jürgen has spent his career working at Deutsches, but with some periods at ECMWF and NSEP as well. And he's going to talk about work that he's continuing in his retirement. Can't be kept quiet.
Thank you very much, Zara. Yep. And I want also to take this opportunity to thank the Newton Institute for this really very nice seminar, and also I want to point to my collaborators. First of all, the opportunity to still do something while I'm on pension. I owe to Bill and Joe from NCAR, and the more practical things becoming later. There were some scientists helping me. That was Sang-Hoon Park from NCAR and Andreas Dobler from the University of Berlin. And those things associated with Williamson tests were helping me. Maria Pila from Deutsches Wetterdienst, actually, she was got a sabbatical to help me for a month, and she kept doing it in her free time on her own computer afterwards to finish this. This is all done with this icosahedral mesh. So I start with the statement that I need uniform. I had already a lecture on that, so I hope everybody is convinced, I did not get a contradiction, that to have a uniform order of approximation in all points, whether it's a pole or somehow irregular, is very important. And I want to take this opportunity to say my specific thing to do. This is what I call the L-Galerkin. It's very, very related to spectral elements, but it is a kind of a concept which emulates all methods I care to think of, in particular the Arakawa methods. And so my way, I didn't do the high order approximation in the full way I can do it. So because when you are at an institute which has an Arakawa method, so I emulated the Arakawa scheme. So all what is real data and a little bit advanced in application is very low order. But when it comes to the high order spaces, it's all simple applications, simple tests. And I will say a little bit on efficiency. The efficiency of these methods is actually, in principle, quite high, but not for the real applications. I didn't test it, but simple applications were done that it's high, and then I say about this method, and I hope I have opportunity to say more about the results. The application is not at that point, but the point you should follow is if there is at least, and I can't prove that a high order cut cell method is the thing to do to give advances in forecast and be very efficient, but maybe there is partial proof of it. So that is a point I want to make. I can't really prove it, but I have some circumstantial evidence in that direction. So that is what I want to do. So this is repetition of what I did last time. There are these numbers which I call L-Galerkin, and I emulate the Arakawa, that is center's difference, in simple ways. I get a CFL of 2.8, that is like in the books. Classical high order brings it down, the CFL, as known, but the interesting thing is that these things I want to talk about, and I hope I have opportunity to explain it more. For example, this one here, order 3, I think always representation order, that is the order of polynomials which approximate the fields. 3 with order 4 different things. It gives nearly 4 as and the Runge-Kutta-4, which I use, has 4 time steps. So the time step is the efficiency from time stepping is really about that of center differences, because I can do these 4 times one after the other. I have about CFL 1, so it is comparable to center difference, even though it's rather a high order. And I get this also. It also says, oh,
so
it is.
How is it that can be higher than the 0101?
One thing is that it's a sparse grid, this high things, and the other thing is that I do the complicated thing, the Runge-Kutta-4, only on the main grid points, the principal nodes,
Okay.
and the other one can do simpler ones. For example, for the points which do only second order correction or third order corrections, they can be implicit, but I didn't even do that way. It is because I did the pre-regularization. So it is, yes, well, when I come to explain it, the pre-regularization operator brings the standard Galerkin procedure gives a little reduction in efficiency, but the pre-regulation gives a higher CFL. So we can't say, so it is a little bit messed up, this thing. So the point I make is normal methods are in the representation order Arakawa and whatever finite elements hovering here around 1, and that's not good enough. So they need superconvergence to bring you up at least to 2, sometimes to 4. And these superconvergence is nice to have, but you have to worry whether it breaks down. You don't have it in all situations. For example, with the finite volume method, it tends to break down if the resolution becomes irregular. So I think that is the reason why finite volume methods always need grid smoothing operation. For example, the Japanese have this spring dynamics with the purpose of making the grid as regular as possible to have the order near 2. And this is the one I want. Serendipity with L Galerki. You can have it in every order. If you go somewhere here, which I did for the cut cells, then you have this scheme. And I can use it to generalize it a little bit. And I did this for the cut cells. But I want to use it here, so I don't need superconvergent. It happens. It goes sometimes to 4th order if I am here only at 2nd order. But I'm not interested in it, because if I am here, for example, at 3 representation order, it won't go lower than 3, and that is a good thing. So I can take any kind of grid. So this is the grids I'm interested for the horizontal. This is a cubed cell. They come all of the same program. If you divide it here at the pole in 3, you have the cubed cell. Here you have something which I think nobody, including me, has used. And this is the icosahedron, which I have used so far. But everything I did here, I discretized also on these rhomboids. So it is actually the same thing as this, technically speaking. It could be derived from the same program. And this is the other thing, the cut cells I'm using. So this is the orography cutting something out of a cell. You can have different approaches. So this is how to do it in high order. There are these high order points. But I didn't do it in high order. That's more an intention of doing it. I don't have these points because I do it low order. Here are the velocity points because it's secret. And then I could, if I wanted, use triangulation, and I have diagnostic points here in triangulation. I could have points here and here, but I could abandon it and use these points. These are phantom points, and that is actually how we did the current implementation, but not the 2nd order points, just this point. So this point is under the mountain, but it determines the field here. But you can have many choices. I find this rather convenient to do it with phantom points. You may have very little impact on the field if the cut is just here, but still you have this point only under the consideration how it determines the field in the inside. So this is these serendipity points, and I want to point on efficiency. Look only at the squares. They are missing out in order 3. And if you count it in 3 dimensions, it's already a rather nice number of points you can get out. I think it's something like 7 against 25. And I have, yes, the question how on efficiency, it's this. This is what we do for the cut cell. You do this leapfrog with sub-stepping. It is, we call it the MM5 dynamics, and we use it in the first version of our model. You have more complicated versions using Range Cutter, but you see complicated operations done, and you need these complicated operations only at the main node points, not at the side points. You need them only here, not here, because here simpler methods are appropriate. Because this is only a third order correction, and second order to the linear field, which is determined by the main node points. So now I come to how I do it. So if you have this kind of hexagonal grid, you have here the point and the connection to the other ones. The finite volume uses this hexagon, which is the dual grid hexagon. And yes, I want to say it looks really beautiful if you plot it, but I don't have any use of it for the Elgalerkin. Because I think if you use these dual grids, then you have fluxes over boundaries, and I didn't find a way to get it to high order. If you take this other grid here, which are the triangles, connecting the triangles, the flux goes along triangular sides. It's actually the same as here, and you can show it's equivalent if the basis functions are linear. That is in the Arakawa case. You can choose them. You can choose this grid and say the flux go along these triangular lines, and it's the same as if they go through the sides of the hexagon. But if you want to go to higher order, you need to have the triangles rather than these. But I want to point to another point. You can have the idea you have sparse grid. You can also have very sparse grid. Look at these. Think the triangles were absent. You have only the hexagons, and you have grid points only at the corners of hexagons and 2 in the middle between them all. Then, if you see the space is more or less empty, you have just a few grid points and many empty spaces in here. So the sparseness of the grid is very much increased, which gives the potential for saving. And I want to point out to the saving which is possible. You save on the physics because you do the physics probably only at the main points. Potential saving is 1/9. You could have 1/27 in this quadrilateral case if you do it also in the vertical. And here in the dynamics, you have in 3 dimensions so few points already in the quadrilateral that the saving is 7 against 27. So it's really worthwhile speaking about. If you do it the same in the hexagon, you have 2 to 27, or if you do it in the 3rd dimension, 2 to 81. And for the dynamics, it's 12 to 81. You can have savings in the time step because of the high Courant number you can achieve. It can range between 1 and 3, and you have simplifications in the time stepping. This gives you also potential savings. I should really point out this is just expectation and things I would like to try out, and I can try out because it can be all tested in play models, which are within my range. So this is limited tested, done, and this works in very simple test cases. But the real test cases are different. So now I come to explain what I understand under L. Galerkin. So it is rather similar what they call CG and DG methods, but it's definitely on the CG side, on the continuous Galerkin side. And so I have a representation order, which is the order of the polynomials inside each cell, and then I have the continuous space. So the grid points determine polynomials, and so S1 is the linear function, the space of linear functions which fit together continuously in spaces, and this is the same to 3. My honest conviction is that it is not reasonable to go beyond 3 at this time in representation or order. So it gives you quite a bit of accuracy. I have also some tests. Then we have the discontinuous space. So if you differentiate this, the continuity goes away, but you don't need to discretize differential operations because you have the function system. If you do it on the order 1 space, you end up with finite differences, with center differences. So you get the normal thing. But here you get more complicated things. And so you need an operator to map this discontinuous function to the continuous one. And this is the Galerkin operator. I call everything Galerkin which goes from the discontinuous space to the continuous one. Classical Galerkin is based on least square, and it's non-local. So the spectral elements and these L. Galerkin methods are strictly local, and that is an important feature for multiprocessing. Well, then you have the collocation operator, because if you form the vector from which you take the divergence, it's normally a product of something. So it raises the order of the polynomial, but you don't want so high order polynomial. So you take these products only at certain grid points and interpolate with your chosen order of approximation again. That is a collocation operator. It's actually used in the same way in the global spectral methods. You have a Galerkin operator, which is called spectral truncation, and you have the collocation, which is the transformation to the so-called physics grid in the global spectral method, and it works also in these local spectral methods. And then I have, this is related to the question which already came, the regularization operator. So this is an operator which makes also derivatives, at least at the main node points, continuous. And it's quite easy to construct such operators. So normal Galerkin is that you go to the discontinuous space and make it continuous by Galerkin. The so-called simplified order 3 is that you go first from the continuous space again to the same continuous space, but it has also the derivatives continuous, and then you differentiate it, and you don't need a Galerkin operator anymore because the derivatives are already continuous. And that is actually the thing which gives better Courant numbers. And perhaps this is the place I got in my last lecture a question of why I didn't worry about these null spaces. And so it takes a time. The philosophy is that if your order is high enough, the null spaces are easily filtered. Some people think that. But there is this school of thought, you can do it in very low order. You can have C-grid finite element spaces. They consist of partially of some functions with a velocity function which is piecewise constant, and the pressure functions are first order, as they are linear. And they fit together very well, and they have the same properties as you would expect in Arakawa secret schemes. That's nice, and if you want to have the same by, for example, taking fourth order and third order representation, that's nice. But I believe in the philosophy that if you are high enough in order, that means in this S3 space, you may not need it, because filtering is very effective, because the range you need to filter is smaller and smaller in weight number space. So, but of course, that is not really proven. I mean, you can have a different opinion, but my philosophy, which I find should give good results, is that you go to the high order spaces. If then you want to have for P in the high order different polynomial spaces, that's of course a possibility, but which I, even in tests, did not follow. Here it shows that if you have the triangular space, it is equivalent to a full grid in the rhomboidal space. And this is actually Baumgartner's stencil. So this is a method of Baumgartner which is used in DWD's global model, which is called GME. So he uses second order stencil. So in this kind of hexagon, you have 7 points, including that, and to determine a second order polynomial, you need 6. So that's done by a least square, but you have only 1 point which you don't need. It's very efficient. So if you do this for third order, you have to go further out, and you have much more than 10 points. You would need 10 points for third order, and this would at least make it very inefficient. And so the immediate generalization from here to here is somewhat not possible. I think it is possible for it is possible if you use these sparse grids. Then of course you lose some of these points and everything becomes more, and there is an ideal Baumgartner stencil, and you can, by using the regularization operator, you can actually use the derivative computed from this or from this to make the scheme conserving. You choose these so-called second order points. I mean, this is serendipity grids. You can have an order of a grid. This is the representation order, and you can choose the equations on these points on the edges in such a way that the whole thing becomes conserving. And I think I have an example about it. So this is how done. Mark Taylor likes to think of it of approximation of the mass matrix. I think of it as artificial fluxes. Or, so this is a flux space conservation. It's quite simple. So you have the grid points here, that's in first order, and you have to define fluxes. So this is a cell, this is a point, and you have the half points and the full points. You have to define fluxes in the dual cell, which go inside, and they determine I mean, the solution in it. That is a finite volume method. So it's essentially in the dual cell. So what I use when I use the finite element of the Elgaler, I take the double cell, and here I have an amplitude, and the mass is not in the dual cell, it is in this cell and in this cell. So this point also has mass in this cell. So they overlap, and yes, this is how it works. You have the amplitude here, and you don't assume piecewise constant function, you assume piecewise linear functions. And then if you integrate to get the mass, you see you have mass at both sides. And this concept generalizes easily to higher order. And this is how it works in high order. You have the main node points, and I like to think of it that they determine a linear representation of the field, and the other is a correction. So you have these differences, and I make, after I have the Galerkin operation here, which is identical or very similar to the Galerkin operation used in spectral elements, I use the Galerkin operation here only for the differences, and may of course be less accurate there. So the field representation is sum over basis functions. The basis functions are here this head function, quadratic and cubic contribution. And of course, once you have this representation, if you have a differentiation, it's obvious how it is you differentiate the functions. So yes, of course, if you have an H field defined here, the mass of the H field is thus the sum of the amplitudes times weights, and the weight, of course, is the integral over the basis function. If you have linear elements only, you can find out that everything is equivalent. The linear basis functions are equivalent to what you do with piecewise constant. So it's equivalent to the finite volume method, but this is easier to generalize to the higher order. So this is now to achieve this L-Galerkin operator as I see it, it is done by introducing artificial fluxes. So a flux on the points, it must not necessarily be the best approximation of the flux function which is defined in the field. It must be defined in such a way that you get a good order. So you do the differentiation of the flux, and you do it correctly for an analytic function, for any analytic function, for any differentiable function, and the difference should be of fifth order if you want fourth order accuracy. So that is the definition, and it's sufficient to prove it if f is a polynomial. Then the whole thing is of high order. So this is very simple example. You do the point fluxes Fp in this way. You take the flux at I plus 1 times 4/3 and plus the average of the fluxes times 1/6, and the same for I minus 1. If you do the difference, you get what it is here written 4/3 times the small difference and minus 1/3 times the large difference, and that is on regular grids classical fourth order. So I think you can derive classical fourth order from a flux-based formulation and get conservation with it. It generalizes to regular squares and hexagons. Of course, it generalizes also to irregular grids, but that's, in my mind, not at all trivial. So then you have to go into the function systems and do this Galerkin operator. So this is just to show how the point fluxes work. And my point is, I made it in the other lecture, that you don't need the regularization operations to achieve that. So Galerkin operator is that you multiply it with the basis function Ej and integrate it. Then you get here the mass matrix and the right hand side, and you somehow approximate it. L-Galerkin, as opposed to this, just gives you point fluxes. You define them in such a way, and you have freedom to do that. Actually, you can emulate the, if you have linear basis functions, the centered differences and the one-sided difference. Of course, as I use Rangakuta 4, I think it goes very well with centered differences. So I use it always to get centered differences. So then I have this zoo of methods where I spoke before. So I use the Galerkin operator G. I use differentiation operators, which are not, not to be approximated. They come naturally in a function method. The regularization operator, which makes a continuous function differentiable, and the collocation operation K, which, of course, this operation makes a difference where you define your grid points. If there is no collocation because your flux function is linear in x and y, then of course the collocation has no effect, and you can choose your collocation points where you want. The result is always the same. As it's normally not the case, the method will depend on where you choose your points. So you could choose them at Lobato points, and then you are probably, at least for the main node points, equivalent to the spectral elements, but you could choose other points. And then is what I call simple third order L Galerkin. So I do the regularization operator on the flux and take the divergence, and I don't need anything. It's already continuous because of the regularization. And this can be used to take any. I showed it for the example of a classical fourth order. You can make any given difference operator conserving by choosing, or you are told what the final difference equations for the second order points are. So you have then standard Galerkin, where you just take the differentiation and smooth it by the Galerkin operation, and you can have these have more than one Galerkin operator in it. So you have one Galerkin operator working on the difference, and then multiply it, have another Galerkin operator, and you actually can use this to have conservation. Actually, Arakawa did this for the simple, for the first order method. But you can use it also in a higher order to derive conservation if the equation is not in conservation form. But I think it's so complicated, it's not worth it. So I'm looking more like at these simple things. So it's not, I think, for this time, it's a bit too complicated, but it can be done if you want.
Question on that before you.
Yeah.
Is there a, maybe not this G here, but there could be a variant of G that if you pull, if R, for example, commuted with divergence operator, you can pull the R outside.
Yes.
So is there a equivalent G operator where div RF is the same as G div F? See what I mean?
It is possible, but I have not thought about it. I mean, it's not impossible to do that.
It seems to me there should be the L Galerkin formulation, there should be a different Galerkin projection that's equivalent.
It is.
And then you can write it in the standard Galerkin.
Possible, but normally it wouldn't commute.
Yeah.
It would be special operators which commute, and I can't often think of how that should work. But definitely those I use don't commute, and that would be a difference. So, this regularization operator is the answer to your first question. That brings the CFL number rather high. So, this is now how it looks, how it works in practice. So here is my target point, and this is for second order finite, for second order representation order. So you have one of these intermediate points always. It's there where in a C grid you would define the velocities, but I think if you go higher than first order, there is no use for the C grid anymore, but you could do it. There is the possibility of doing it. So you have this stencil, this point, it's neighbors, and it involves this stencil, which here 3 points in each direction. In a third order scheme, you would have 4 points in each direction, but the middle is always the same. And one of the points to observe, if you think it has only 3 branches, that is the case if you have the hexagonal grid as a corner grid. This is very sparse. Then you would just have 10 grid points on these 3 branches if you have 2 on this side. And that is the ideal to derive Baumgartner's third order stencils. You can differentiate it here, and the divergence here can be projected outside to equations for these degrees of freedom in such a way that whatever mass you lose or gain here is somehow stored here in a kind of way. So, but the point, for the practical point of view, I mean, if you want to introduce it in a practical method, you get quite normal difference equation. You can formulate it as perfectly as a difference equation. You get the time derivative at this red point as a sum of weights times this. And I think if you have a model which is programmed in C++, which I probably will never learn in my life, you still could put such an Elgar-Lurkin method in there by just communicating these weights and asking the person who owns the model to put in these weights here. It's the most simple finite difference formulation conceivable. That you do it. So then you need what I call the weight factory. So this can be done independent of any model. So you use this theory to compute the weights. You need as input a list of all neighbors and the coordinates of neighbors. And then you need as another input the choice of the method you use. For example, simple O3 or standard Galerkin O2 or whatever. And this gives you, no. Yes, this then gives you these weights. And you actually don't need to know anything about the model to put it in. That is, of course, a nice interface. I was always used to think of interfaces. If you have different approaches, it's a nice feature that you can put in a numerical method into a model which you don't know by just asking the person who owns the model to do a simple finite difference equation with weights, and he gives the table of neighbors, and you compute outside the model using this theory the weights, and the person who owns the model doesn't really need to worry what kind of basis functions there are. He just gets the weights and it should work. So the framework is such: if you have O1 on an O2 grid, you can have all Arakawa schemes in this framework. And I use this because my Katzel approximations at the moment are on the Arakawa C grid. I would like to have them on a higher order grid, but whatever. Finite elements can be used and they can be simplified using the Galerkin process. The same is for the spectral element. I think it's lower order, but maybe not. You can have it in any order, but if you use order 2, for example, it's already higher in accuracy, but I think only on regular grids. So therefore, this gives the order 2 spectral elements gives an enormous accuracy on regular grids, but I think it goes away of irregular grids. Therefore, I like the order 3. And the finite volume you can have, but I think I don't see any way of putting the finite volume approach to a higher order in a practical way. So this is one, I think. So I now can go to, I already said something about efficiency to some applications. So the high order points don't need physics. So I think these are my points, and I have these high order points here in the middle on the sides of each triangle. And I think it would be reasonable to do the physics only here. And you also can use cheaper methods. So if you have a multi-step method like Rangakuta 3 or Rangakuta 4 with sub-stepping here, you don't need it here. Simple implicit integration here would be sufficient, and you get the main part of this amplitude by linear interpolation. You use only the second order part by another Galerkin procedure. And yes, the other point for efficiency I use in the results, I show straight lines here. So they are, of course, don't give a totally regular grid, because you see there is considerable irregularity here. But it is, of course, good for efficiency if these points line up on a great circle. So this is a difference. So this is order 2 standard. So you see this is a grid interval from 1 to 1. That's a cell interval, but the cell has in order 2 points. And you see it goes up and down within one cell. So this is the smallest positive function you can define here. And it is still relatively accuracy for the small scale it has. This is same for third order, and you see it goes up and down in 1/3 of the grid length. It doesn't reach the half grid length here, and so it is there not so efficient, but it may become again soon efficiency if you do the scale a little bit larger. But the point you see here rather obvious, that it goes more than one grid cell. That means more than 3 grid points in one time step. That is a rather high CFL. So the high CFL somehow works. I should actually mention one other thing. These serendipity grids are not stable always if the one-dimensional case is stable. So there are well-known cases in 2 dimensions which are not stable if one dimension is stable. One thing is semi-Lagrange with serendipity interpolation. It just doesn't work. So you need 2-dimensional test cases for all things. So I did some 2-dimensional cases. So this is actually third order on the sphere, and it's a divergence field without any smoothing operation, which doesn't work very long. It doesn't work very long, so it works only for 2.5 hours. So it needs artificial diffusion. But it is very nice. You see that the grid has not the same periodicity as you see it here, for example. You must really look carefully. This is Williamson's test number 6, and I don't at the moment know what resolution it is. So this is the same test case after day 3. And you see also it is rather periodic, and the high order makes that you don't see anything of the grid, and it's a not smooth grid. So some people like Tomita smooth this grid by spring dynamics, and it's not necessary here. This is a convergence diagram. So resolution against thing, and this is a third order rate of convergence, and it's also for Williamson test case number 6, and you can do it only for short time integrations. I think it goes up to day 5, because the case 6 of Williamson is already unstable. It was also shown theoretically by Subborn that it is unstable. You can't predict this test case infinitely. It will eventually lose predictability. And so now we come to the boundary. This actually interests me. So it is a second order representation scheme. But in the boundary cell, which is here, it's shallow water, it's first order and either extrapolated, so I don't have prediction on the surface because I want to have a small cell here. If I extrapolate linearly, I get this, and after reflection, I get nearly the same. It was here a little bit less amplitude, and it is somehow reasonable. If I extrapolate piecewise constant, I would get this, which kind of worries me, because I would rather like to extrapolate the functions here. So it depends very much what you do at the boundary, what you get for reflection, and that is one-dimensional shallow water. It's not really very complicated. This is with second order circular wave. It remains circular. That is because of superconvergence, because if it would be only second order, it would have would be not so circular symmetric, and it gives a nice reflection. And this is actually a reflection on a line which is here. So this is initial, and there is a wave going out and back again until it's again reflected at the same. That works actually quite nice. You see here there is some dirt where the reflecting boundary was, and the reflecting boundary can be at any place between the grid cells. So this is how it works, the real atmosphere. These are idealized cases. This is a 2,000 meter high mountain, and it goes here and has a circulation. This is temperature. And this is with the terrain following. It gives this feature, and you get something totally different. It's nearly a two-dimensional flow around it in the temperature field when you use the cut cells. And if you put on radiation, it looks totally different also from this. So there is big impact on the flow, and this is the atmosphere at rest, which of course you can't plot with because it's just constant, because the cancellation is exact. So people tell me that their model is not so bad as this, because it goes up to 1/3 of a meter per second. But this shows how it should be. It goes lower. These are centimeters per second on this scale. It's much lower. And that is the cut cells when the radiation is switched off, day and night time. So these are physical flows called by radiation, and I think this is a kind of accuracy of pressure gradient cancellation we should aim for. That the false velocity r in the area are lower than in the centimeters per second. So this is and this is how to put it in practice. This is actually a real run with real data, a cross-section through the Alps. So you see what the cut cells are by that the orography is not filtered. It has this very high peak, but it has filled out the V-valley. It is actually not necessary for dynamics reasons, because what the dynamics does, it treats a very deep valley with no side points as a one-dimensional model. There is no dynamics in it. It doesn't have any horizontal exchange, so it remains a one-dimensional model. But the physics routines we have wouldn't support it. And even if we do only one-day forecast, the data analysis doesn't accept these points, because the data analysis does a long run. And if a point is there which never gets data, it will approach 0 Kelvin or the temperature of the sun. Our radiation is not that good that it can support a one-dimensional model forever. So this is the reason why we need to fill the V-valleys. And maybe I should point to another thing. The physics is done on a finer grid. So the physics is done on the terrain, on the old grid, on the terrain following grid. And it runs there independent, and it's only interpolated from dynamics to physics. Yes, these are independent, but the dynamics gets the physics tendency by interpolation, but not the other way around. So a boundary layer which forms here in a fine mesh will stay there. And that we don't need, actually the NASA model does the same. And they have called a thing like grid connection, which we don't need up to 5 days. So after 5 days we see blow-ups. But in the short runs of 1 day, we just didn't need any two-way interaction of these. Just that the physics tendency were given to the dynamics grid, not the other way around. So the physics grid developed independently and didn't lose its scale. It's not done that it's always interpolated so that the structures in the physics are disappearing. This is actually now a 5-day run. And this is 5-day runs covering a month over a relatively large area. And that's interesting. This is actually one 5-day run. And this is a vertical velocity. This is Z. Z is the old scheme. And that is what I call verification. Perhaps I should say something about verification, because vertical velocity is obviously not observed, but it is somehow diagnosed, and in our analysis scheme, to get 0 at t equals 0, you get vertical velocities. They are done by solving the omega equation on some smooth surfaces. And it's very complicated, and it's in our manual. But if you think that is something like analysis, that is a 5-day forecast, there is some verification possible. It is similarity between these here and here. The structures have a good similarity, so that they verify. The verification may not be brilliant, but the vertical velocity verifies. Here it doesn't. It may have also this, but the amplitude is totally wrong, and also there are noise features everywhere, so that it's not really reliable. The interesting thing is how far it goes to the ocean. And we looked after it, and it actually goes to the ocean in 2 hours. On the equator, from these mountains here. It just spreads out very, very fast. And of course, it depends that the moisture treatment here, it was the first time, not only we say the first time that our model, which was used in the, rather in the north, was used in the tropics. So it had, but this obviously must have impact on the precipitation, and it does. So this is a precipitation of the operation run. This has been improved now, because this is now a national climate model, and the precipitation has been tuned to be not so bad. Unfortunately, we have verification only over land, but you see that it's really nice how this over China gets. The dry areas here are not quite dry, but much drier than here. And so, for example, this here is in the right position, more or less. It's not wrong in the amplitude, but also in the wrong position, because it doesn't have precipitation at the coastline. It has it in the interior, where there is no precipitation. And we did the same calculation with the newest version of this model. The amplitudes are much better, but this position error is exactly the same. Also the same that here is a point of precipitation. It's a bit here and not here. It's totally wrong position, this strong precipitation. Yeah?
One observation, this is very interesting. The effect of resolving the orography.
Yes.
And the one thing which will be very useful. This data, you started the run on a January initial condition. January.
Yes.
It will be very interesting to see during the monsoon season, the southwest monsoon season. That will be May and June.
Yes.
If we make the simulation for May, June, July, during that time, it will be very interesting. A lot
Could be
of activity-
absolutely right, but this somehow was the maximum I could do
Sure,
myself.
sure. It's interesting.
I am on the lookout for, it's essentially a problem of funding. So this more extensive work of this, which I would very much like to have, is a question of funding, and unfortunately this is very difficult because yes, anyway, it's a question of funding. So I personally can't do more than this case because it took much more time for me than I expected.
What I meant was that, like when we run the simulation during that period, there's a lot of activity happening in the tree during that period. So it will show, all the
Yes.
interesting things will show during
It would be really interesting to do it, and would also interesting to compare, to bring both models from the physics standpoint up to date. And I was told by Axel Seifers, who does this kind of physics things, that it's just two parameters in the model which are responsible for the bad precipitation here. So you can change them here as well. But yes, as much as I would like to do it, but it's really a question of funding. So maybe we find a way to do that. I totally agree that it's interesting and one should do more about this. So
before you leave that one, so you're running the exactly the same parameters in the physics for both those
yes,
two cases? Because why is there so much pervasive precip all over the ocean?
it is coming. I mean, we were following it in half-hourly intervals, and it's coming in 2 hours from this area spreading here. It is,
But it's
of course,
pervasive everywhere. I mean, it's along the southern boundary, the eastern boundary.
yes, it is also going very much to the south, and it spreads then from the equator. It spreads first through the equator, and it spreads from the equator very fast north and south. That is a bit surprising that over these large ocean areas you still have the effect of orography. It's surprising, but
It's more than surprising. I think that
you think it is wrong?
suggests there's a problem. Yeah.
No, I mean, we looked at it. Actually, the referees of the paper we published is asked the same question, and we were in the end able to convince them that it's very fast spreading waves coming from the mountains. So, looking at it in the time. So, but yes, I totally agree, one should look more at this. But it spreads out surprisingly far out.
It sounds like.
But it may of course depend on the strong precipitation. So this is oversensitive to convection. So immediately if there is a little vertical velocity, it starts convection. And convection starts heating, it makes more vertical velocity, and it makes more convection. So that is why the convection starts out very fast. So maybe the answer to that would be to change these two models to the current version of this model.
What's the reason for this rapidly propagating disturbances? Is there some significant imbalance in the initial state that sends off these?
Yes, I mean, there are certainly going something like gravitational waves out of it, and the gravitational waves trigger convection. And the convection is very strong.
Right, but
And it makes more vertical velocity, and so it's gravitational wave going out and amplified by condensational heat. So the wrong thing here is that, of
You're
course,
saying you had that rapidly expanding wave is much more significant in the train following.
yes.
So there must be something very different in the initial balances of the,
Oh yes, it is starting out here, because if you go back, the vertical velocity are soon becoming very different. So they start, of course, to be different here. It doesn't come from here, it comes from here, because there is much moisture in here. And the moisture put in energy into these gravitational waves. So if there is a wave and the wave has a vertical, produces a vertical velocity, it immediately starts convection, and the convection is not is producing more convection. I mean, that we saw in the time development of this thing. But the problem is entirely with this model. It's not with this model. And it has been solved with this model. I mean, we don't see these strong things. We will probably see, yes, if we do it what we call the correct physics, that means the physics tuned towards this, we will probably also see less vertical velocities. But I don't know. It would be interesting to see.
Can I ask the question I had earlier, but now it's more pronounced. How big is the grid scale on these computations in comparison to these features of the solution?
Oh, the grid scale is 25 kilometers.
And these kind of...
they are not grid point storms.
No, I know they're not grid point storms.
So
but
they are...
how many grid cells, like these kind of complicated features there?
They are having several grid cells here, because, I mean, this is not 25 kilometers, it's much over. It has at least 100 or 200, this feature.
My question was, do you actually observe the theoretically discussed high order convergences here? Because, I mean, this is highly irregular.
No, convergence tests can't be expected if you have real orography. Just then. Therefore, we didn't use Williamson test case number 5. It already had a non-smooth mountain in it.
So my question is, for these kind of computations, would you advocate high order? Because that was your talk's title.
Oh yes. I mean, it is, the high order brings better, it is not necessary, it works with low order also. But the high order does better transport. And I don't think it can do any harm if the clouds are transported correctly.
Well, apart from costing more.
Apart
from costing more.
No, I actually pointed out that this high order is at least of the same cost. It is at least for free, but it may even, because of the sparseness of the grid. So if you do square grids, you have sparseness of the grid, and you have simplified treatment of the high order points. So that wouldn't cost you more. It's actually a cheap method.
So you trade grid sizing versus high order.
And I would also, if it goes towards high order, I would not suggest to compute the grid where the physics is working on in high order. Also not the orography. The orography should be smooth on lengths of 3 delta x. So the orography comes only at the main grid points. So that all would kind of interact with your question, because the dynamics needs a smooth grid. That's a high order, and the dynamics as a whole can work. So it gets a smooth grid by doing the physics only at the old grid. And then you say what it costs to put in these extra grid points. I mean, it's all expectation, because this kind of model has been done only with low order. But the expectation is that perhaps you get a 3 times increase of grid length in 3 dimensions by a factor of cost of maybe 5 around, which is So can make the grid a little bit coarser and still have overall a finer grid than before. And so it is really cheap, this one. So it is not like we heard with the DG methods, where you have to invest much computational effort.
Well, but in DG you can also make a coarser grid and maybe more coarse. So I think it's
yes, but
still an
it
open
was compared with grid length of the DG. So if I compare here with the grid length of the high order grid, these methods are cheap because of the sparseness of it and of simplifications and of possibility of high Courant numbers. So it's not, I mean, it's actually, but if you ask for solid proof, I would have to program this model in high order. And that is, but here we see mainly the effect of the mountains. So I hope I...
Sorry, I was going to say we've already run over, so maybe we should wrap up. Could you think you can wrap up in a couple of minutes and then we can carry on talking
Yes.
about coffee?
So we had this, I just say, there is impact on scores. This is error against radiosondes, so they are improved by a third of the degree. So that is really nice, and it raises, I mean, raises my expectations that this method really has an impact on forecasts. This is another case of precipitation improvement. You see that's the front. You see now the orography front moving over here, and it's somehow like observations, and here it's somehow fractal. And that is not in the tropics, so we don't have that problem of tropical energy going into the gravitational wave, and that is my wrap up. Thank you very much.
Thank you, Jürgen. Yes, shall we take questions upstairs over coffee, given there's been a lot of discussion already? Thanks.